Hi, Professor. This talk is our final presentation.
My name is Yu-Hsuan.
And my name is Cheng-Yen Wu. We are from Institute of Biomedical Engineering. The research field in our lab is focused on gas sensing by semiconductor device. However, our lab is emphasizing on the device characteristics improvement and the sensing materials research. And there is less study on the measurement signal and relating circuit application. So our final presentation will focus on circuit application on sensor signal. And the topic is a 0.7 volts capacitance to digital converters for interdigitate electrocapacitive vapor sensor. And the author is from the Department of Electrical Engineering, National Cheng-Yen University. And the odor detection can be applied on many aspects. For example, air quality, healthcare, industry, or military application. There are many types of gas sensors can reach our research goal. Among these sensors, capacitive sensors are widely used because of the better resolution and sensitivity in sensing vapor displacement, pressure, humidity, and acceleration. Besides, the power consumption of capacitive sensor is less than other types of sensor. This best theory of the capacitive sensor is that the value of capacitance will change in proportional to the target, which means the sensor can change from the signal when it detects the gas target. And this page is the outline of our presentation. And the first, I will give brief introduction of sensor. And the second, I will introduce the block diagram of the proposed circuit and discuss the features of each sub-circuit. And finally, I will conclude my talk. And this figure is the interdigitate electrode, and the polymer will coat on the electrode. This type of sensor is depending on the permittivity change and swelling of the polymer when the target flows through the surface of the sensor. So the value of the capacitance can be concluded as this formula. And N is electrode pair numbers, and S is the space between adjacent electrode fingers, and S0 is a vacuum permittivity, and S1 is relative permittivity. And in this paper, they operate the SAR ADC at 0.7 volts for the interdigitate electrocapacitive sensors. And this figure is a block diagram of the proposed capacitive to digital converters, CDC. And this sensing step can be divided into the three parts. And the first is sensor, second is capacitance to voltage converter, CVC. And the last part is successive approximation, resistor, and analog to digital converter, SAR ADC. And the CDC circuit with switch capacitance converters have been proved to achieve high resolution. However, this type of interface is high power consumption and low dynamic range. With correlated double sampling (CDS), the capacitance to voltage converter (CVC) generates two voltage and 2 with upside polarity to fit the differential successive approximation resistor analog to digital converter SAR ADC, which will change from the voltage into digital value. And the SAR ADC employ a dynamic comparator which doesn't consume any static current, so the power consumption is relatively slow. And these figures are the schematic of the capacitance to digital converter CVC. It can be divided into 4 steps, and the figure A and C is preset consumption, and the final is turned on. In the figure A, the reference capacitance is grounded. Sensor capacitance is connected to the VDD, and the figure C is in contrast. And the figure B and D is sample mode, and change from the conditions from the A and C respectively, and the fire is turned off. In the figure B, reference capacitance is connected to the VDD, sensor capacitance is grounded, and figure D is in contrast. And as for the correlated double sampling, we can understand it via this flowchart from the reference paper. And the center node is set to virtual short through the negative feedback configuration of the amplifier. And the readout process then extract charge proportional to the difference between the sensor capacitance and the reference capacitance, and store it on the sample capacitance. When the circuit changes from the pre-charge 1 to sample 1, the voltage value at the center node will relate to the capacitance transients, so we can get a relation of the V out and the capacitance. And for the sample 2, the role of the sensor capacitance and the reference capacitance is switched, so the output is equal but the opposite polarity. And the amplifier in the CVC, we can get this schematic. The amplifier upright or not will depend on the fire and the condition of the M0. When the fire turns M0 off, all the transistors will be in cutoff region, and the amplifier sleep without static current. When the fire turns M0 on in sampling, which will wake the amplifier up. And for the successive approximation resistor analog to digital converter, this is the circuit diagram of the SAR ADC. And it consists of 2 switches and 2 capacitor arrays, which are controlled by the larger circuit, function as the DAC. And the comparator acts as an analog to digital converter. These 2 arrays are assembled capacitors in previous CVC circuits, and the ADC will repeat comparison of 2 voltage and switch off the lower voltage on 1 until the least significant bit decided. And as for the operating rule of ADC, we can use this flowchart from the reference paper to explain the mechanisms. And first, the V in positive is larger than the V in negative, so the D out is 1, and the V in negative will change to the V in negative minus 0.5 V reference. Then compare to the next best. When the V in positive is smaller than the V in negative, the D out is 0. And the ADC will repeat this rule until the I equals to the number of the capacitance pair. And continue to the last page. There are 2 types of switching procedures. One is conventional type, and the other is a monotonic type. And the proposed switching sequence doesn't require upward transition. At the same transistor size, the 1 resistance of a NMOS switch is only about 1/3 that of the PMOS one, having no upward transition speed up the DAC settling. In addition, since sampling is done on the top plate, the comparator can do the first comparison without any capacitor switch. And for a n-bit ADC, the number of unique capacitor in array is 2 to the power of n-1. It is half that the conventional one. And the schematic of the dynamic comparator in the SAR ADC is shown in this page. This consists of 3 parts, and the first part is preamplifier, the middle is dynamic latch, and the last part is NAND latch. And the function of these 3 parts of the circuit, and the preamplifier decreases the effect of kickback noise, And the dynamic comparator has no static current. It is suitable for low power consumption device. However, and the speed of this circuit is relatively slow, so the NAND latch comparator will increase the comparator speed. And finally, I will give the conclusion. Successive approximations appear to be an excellent solution for CDC circuits. The power consumption is relatively low because SAR ADC employ a dynamic comparator that doesn't consume any static current, and the capacitive sensor can change from the signal of the pressure or other sensing targets into capacitive quantities. And all about is my final presentation. And thank you for your attention.